Hello, ladies and gentlemen. It's Matthew Farrow here again, and welcome back to my space. This is the fifth video in the series of videos where we explore ways to compute the limits of some functions without the use of L'Hopital's rule or even the series expansion. So far, we've solved the first four problems on this problem set, and we are now going to see how to attack this last problem on the problem sheet. Let's get it started. Yeah, for this last question, again, as usual, when we try direct substitution, which is always the first thing to try, we'll plug in x equals to 0 into the expression. So we have sine 5 times 0 minus tan 5 times 0 over 0 cubed, which is sine 0 minus tan 0 over 0. And that is 0 minus 0 over 0, since sine 0 and tan 0 are both 0. And this is equal to 0 over 0, which is an indeterminate form. Although this is enough grounds for the usage of the L'Hopital's rule, we have learned so far in this series that we can actually avoid the use of L'Hopital's rule by playing around with the trigonometric identities and this basic fact. So before we carry on with evaluating this limit, let's look at one new fact that we have not seen, which is actually a product of this fact. So, and that fact is the limit as x goes to 0 of tan x over x. Okay, so how do we find this limit? So let us use this identity that we have here. Tan x equals to sine x over cos x. So it means I can rewrite this as the limit as x approaches 0 of sine x over cos x divided by x. And this is the same thing as the limit as x approaches 0 of sine x over x times 1 over cos x. Since this is the same thing as the limit as x approaches 0 of sine x over cos x times 1 over x. So the x and cos x can switch places for us to have this. And as you can already guess, all we just do is to split this into limit of sine x over x times the limit of 1 over cos x. And by our fact, our almighty fact, so this is equal to 1. And if we plug in 0 here, we have 1 over cos 0. So the answer is 1 times 1 over 1, which is equal to 1. In other words, we have a new fact born from the old fact that the limit of as x tends to 0 of tan x over x is also equal to 1. Mind you, it should be noted that this is only true for sine x and cos x, and tan x rather. For cos x, it doesn't hold. So maybe I should also put that disclaimer here. The limit of as x goes to 0 of cos x over x actually does not exist. It is not equal to 1 like the others. All right, let's come back to the question. So let me shift this work downwards and come back here. So we have successfully seen that there is no way to go with this one. So let us now start our usual manipulations. So this cannot be factorized, you cannot rationalize. Well, maybe if we do conjugation, it could work. But one thing that we can do, so let's see. So the limit as x goes to 0 of sine 5x minus tan 5x all over x cubed is equal to, so we can use this formula here to rewrite tan 5x as sine 5x over cos 5x. You'll see why this is useful in a moment. So this is sine 5x minus sine 5x over cos 5x all over x cubed. Now that shows us that sine 5x is common in the numerator, so we can factor it out. So the whole idea is to somehow get something that will resemble our fact. And I know that if I can get sine 5x over one of the x's here, then something is good. So we have sine 5x into bracket, we're left with 1 minus 1 over cos 5x all over x cubed. Interesting. So this is the same thing as the limit of sine 5x over, so I'm going to take one of the x's in this x cube, put it here so that it gets closer to what we want. X tends to 0, and in the other bracket I have 1 minus sec 5x again over x squared. So we know that 1 over sine theta is equal to cosec theta, and 1 over cos theta is equal to sec theta. 1 over tan theta equals to cotangent of theta. So if we have 1 over cos 5x is equal to sec 5x. Good. So we can now split this up into two limits. So limit as x approaches 0 of sine 5x over x times the limit as x approaches 0 of 1 minus sec 5x over x squared. Now, if we try to do direct substitution at this point, we know this will give us sine 0 over 0, and sec 5x is the same thing as 1 over cos 5x. And if you plug in 0, that is 1 over cos 0, which is just 1 over 1. So this is 1 minus 1 over 0, that is 0 over 0 as well. So it means we can come up with more magic tricks that we've been seeing in the past 4 videos. So for questions like this that are very, very close to our basic fact, the trick has always been you multiply both the numerator and the denominator by something such that the numerator here will be exactly the same thing as what is inside the bracket upstairs. So, and that means we want to do the x tends to 0 of sine 5x over x times what? Times 5 over 5. Because 5 times x will generate 5x that we need for those two things to be equal. Let's generate more space. Then we also have the second part, the trick that we've been using for stuff that looks like this is to multiply by the conjugate. So, and the conjugate here is, so we multiply by the conjugate of 1 minus sec 5x. So that will be times 1 plus sec 5x over 1 plus sec 5x. Now, I can rewrite this as the limit as x goes to 0 of sine 5x over, then we have 5 here, we have the 5 here, and we have successfully introduced 5x, that's the same thing as what is here. Then times, on the other side, x goes to 0, we use our usual difference of 2 squares. That gives us 1 squared minus sec squared 5x all over x squared into bracket 1 plus sec 5x. Yes. So at this point, 5 can come out. Since it is a constant, we have 5 times the limit as x approaches 0 of sine 5x over 5x. We are happy because that is exactly what we want. Times, so one of the trigonometric identities, in the Pythagorean identities, is that tan squared theta plus 1 is equal to sec squared theta. So it means that 1 minus sec squared theta will be the negative of tan squared theta. So if I have tan squared x plus 1 is equals to sec squared x, when I move the positions, or when I switch the positions of these two, this goes here, this comes here, we have that 1 minus sec squared x is equal to negative of tan squared x. And how does that help us? We can already see here that this will produce negative of tan squared 5x over x squared, then times 1 plus sec 5x. And this we already know to be equal to 1. So as x goes to 0, sine 5x goes to 0 and 5x goes to 0. So that is basically our fact. So this is 5 times 1. Then we can cleverly change what is going on here. So this is the limit as x goes to 0 of minus tan 5x over x squared. That gives us this part of the fraction. Then we're left with times the limit as x goes to 0 of 1 over 1 plus sec 5x. Now we are getting close to the end. So for this just becomes 5. And for this one, we have already seen how limits can pass power. So this is minus the limit as x approaches 0 of tan 5x over x squared times, so this I can already do the direct substitution. So this will be 1 over 1 plus sec 5 times 0, which is 0. Then using the same trick I used for sine 5x over x, I know that this will be 5 times minus the limit as x goes to 0 of tan 5x over x times 5 over 5 squared times 1 over 1 plus 1. Since cos 0 is 1, 1 over cos 0 will be 1 over 1, which is 1. So that means sec 0 is 1. So this is equal to 5 times negative of 5 limit as x goes to 0 of tan 5x over 5x squared times 1 over 2. And finally, we can apply the identity, the fact that we proved at the beginning. So this becomes negative 5 over 2 times, so I've done this times 1 over 2, times 5 times 1. So what I've just used is this fact here. So when we have the same stuff here and here, the limit will go to 1. So this is 5 times 1 squared. So this is going to give us minus 5 over 2 times 25, which is equals to minus 125 over 2. Phew. And with that, we've come to the end of the problem. So what we have achieved is being able to evaluate this limit without the use of the L'Hopital's rule. If there are any questions or there is any need for clarity, do not hesitate to drop your questions or comments, observations in the comment section below. Thank you. Till we meet again, stay mathematically happy. Bye.